Dear ladies and gentlemen, warm greetings from Switzerland and welcome to this Home Trainer webinar. My name is Ilja Tsikur. I am the host today for this webinar. I am Senior Engineer for Global Sales at Kissoft. And beside me sits Mr. Hanspeter Dinner. He will be presenting to you today the new ISO 6336 2019 edition and its changes and consequences and implications for you. Now, before we start, I would like to give you some general information about Home Trainer webinars and also Kissoft webinars that are to follow. So, due to the current situation with the coronavirus, and since many people are also working remotely, this is also an opportunity to educate ourselves in these difficult times, and this is one of these webinars where you have the possibility to learn something new about the ISO standard. In general, if you have any questions to the Home Trainer webinars, or if you want to see what is scheduled or what is coming up, you can also contact Home Trainer at gleason.com, or you can just go to the Gleason homepage, gleason.com, and under trainings, you will find the possibility to register yourself for different webinars that have been scheduled this year. You see, there is actually a lot of topics that will be covered in April. For example, the next Gleason Home Trainer webinar is on 16th of April, which is basically about gear pre-machining considerations for better hard finishing process. So you see, we have a lot of topics that cover gear design, that cover gear manufacturing and also inspection. So use this time that you have right now to educate yourself, and you will find all the information on the Gleason homepage. In addition, I would like to point out our new Kissoft homepage, kissoft.com. There you will also find a section which is called Web Demos. And there you will not only find the information to the current webinar, for example, such as the video of the webinar. We are actually recording it right now and going to publish it next week. But you can also have a look at the past web demos if you wish to have a look at the topics we covered earlier. Now, regarding this web demonstration today, you have on one hand the PDFs, so this presentation of mine, but also the presentation about the ISO standard available for download in the tool itself. You can also ask questions during the webinar. There's a special section for it, which is called questions and answers. Some of the questions I will maybe address at the end of the web demo. Some of them I'll try to answer also live. Yeah, and the recording of the webinar is going to be available soon as video, probably next week on our homepage. So if you missed something or want to have a look at it again, there will be a possibility. Important is also that the ISO 6336 2019 edition will be available in Kissoft release 2020, which is actually scheduled and release is scheduled end of June. And with these words, I would like to give the presentation to Mr. Hanspeter Dinner, and he will present you then the topics about the ISO standard.
Ladies and gentlemen, welcome to this presentation on ISO 6336 2019 revision. My name is Hanspeter Dinner. I'm Director Global Sales with Kissoft Company. I've been with Kissoft for about 16 years now, on and off. Some of you may have met me in a training or when I was visiting your company. It's a pleasure to share some time with you online. I'm sorry you can't see me. I'm sorry I can't see you. Still, it should be an interesting presentation as this topic affects all of us. Since 1969, the ISO 6336 was in place, and it is considered as one of the most influential standards in gear design. Originally, it was based on DIN 3990, Most of the basic concepts and formulas were originally from that German standard, but it has undergone some modifications and revisions. The first revision was in 2006. Then in 2008, there was an important corrigendum regarding the influence of the helix angle. Now, in November 2019, the latest revision has been released by ISO. What is the scope of today's presentation? We will first look at the current situation, like what is affected, what is the status of this standard. Secondly, I will mention briefly how is the status in Chrysoft software. Then we will give an overview of the changes, focusing on root strength. Fourth part, we will look at this new factor F epsilon. Section 5, we will look at how the form factor YF changes for internal gears manufactured by a shaping cutter. Point 6, we will look at the changes in the helix angle factor Y beta. These three sections, 4, 5, 6, cover topics that affect the calculated stresses. Whereas in section 7, we will look at one particular change on the permissible stress side. In section 8, 9, and 10, we will then look at a few examples where we have taken wind turbine gearboxes, an EV transmission, and examples from the technical report 633630. We will calculate them both based on the prior revision of ISO 6336 and the current revision, and we will compare the results to get the feeling, is these relevant, these changes, or less so. Finally, we'll give an outlook on how to use scripting function in Chrysoft to automatize such tasks, and we will conclude with a conclusion, obviously. You will then have some time for questions and answers, and I'll be happy to share opinion with you. It is to be mentioned very clearly that if somebody talks about ISO 6336 in its entirety, then only revision 2019 is the only valid revision. All other revisions are withdrawn. If you look into www.iso.org, which is the official homepage of ISO Standardization Bureau, you will find that if you search for ISO 6336 2006 revision, you will get an indication that this standard has been revised, which means it is also withdrawn and replaced by a later revision. This means for you as a designer, as a purchaser, or as a supplier of gearboxes, that contractual documents used in the purchase or sale of gears or gearboxes or similar products that reference to ISO 6336 technically refer to the current revision, which is 2019, unless in said contractual documents reference is made to another revision explicitly. This means documents formed under a contract referencing to ISO 6336 means calculation reports, specifications, or certification guidelines should be either specific, means they should point to a particular revision, for example, 2006 revision, or such documents should be updated or rediscussed to be clear to both parties which revision of the ISO 6336 shall apply. It remains to be seen how this revision affects our designs, affects business between gearbox supplier and purchaser. You will have to go through a learning phase. For example, we will see that some of the ratings will go down, others will go up. which means that your gearbox size will change if you apply these new rules. And the general recommendation that we give you, we recommend to gain experience by using this revision in parallel to the 2006 revision. Basically, do all the calculations twice, do it with the old revision 2006 that you're familiar with, do it with the new revision as well, which you are not familiar with, compare and assess the results. That's the basic recommendation. Now, what is the panorama that we are looking at? ISO 6336 is actually a family of standards, or a standard consisting of several parts and technical specifications and technical reports. In this image on the right side, you find that part 1 to 6 are parts of the international standard, except for part 4 on two flank fracture. That was added only recently. Then part 20 and part 21 are actually technical specifications. These were formerly the technical reports 13989 part 1, the scuffing rating with flash temperature method, and ISO TR 13989 part 2, the scuffing rating with integral temperature. These are now also part of the ISO 6336 series. Also included was the ISO TR 15144 part 1 on micro-pitting load capacity calculation, which is now also part of ISO 6336 family. And then there are two technical reports, including example calculations using the formulas described in ISO 6336 parts 1 to 6, and on the technical report 22 on micro-pitting. These later examples in part 30 and 31 you may use to compare the output of your software to the standardized results as a first verification of a software. The standard family 6336 is managed by ISO Technical Committee number 60, Subcommittee 2. Different countries like Germany, US, France, UK, Switzerland are involved in revising and writing and managing these standards. Dr. Kissling, president of KISSOFT AG, is the head of the Swiss delegation to the ISO TC60, and for the last 4 years I have been assisting to him. In this presentation, we mainly focus on the root strength for two reasons. Number one, a failure in the root is usually catastrophic, means it leads to an immediate failure of the whole drivetrain, and typically is harder to predict or to detect in field maintenance operations. Second reason is that most of the bigger changes in this new revision are related to the root strength. Still, we need to give a few comments on the other parts. Part 1 on the principles. There is one important change that can be considered as more of a correction. Basically, in the past, it used to be such that KV factors did not have a limitation. We had one case where we had extremely high circumferential speed in gears, where KV, as per the formulas, became a value like 99. This is now limited such that KV does not exceed more than 2. So if KV is calculated as per the formulas, the result is higher than 2, then it is set equal to 2. That makes sense from a physical perspective, because any value of kV higher than 2 signifies that the flanks would separate. Once the flanks separate, torque transmission is obviously interrupted. There's no more load, so it does not make sense to use a value of kV higher than 2. This restriction has been implemented in Keysoft software for some time because it is obviously not in line with physics. You used to get a message in Keysoft that kV should be limited to 2 as a manual input. A second comment outside of the root strength calculation, a comment on part 2 for the flank strength calculation. There, a new auxiliary factor FZCA is introduced, influencing the contact factors ZB and ZD. In this presentation, we keep this new factor FZCA to 1. That is for helical gear sets with suitable modifications in profile and lead direction. This means that in the course of this presentation, the results on the flank do not change, since we want to focus on the root strength. This factor FZCA, there's a table in the part 2 of the ISO 6336 revision 2019 that distinguishes between 3 cases. First case is we have suitable modifications in both directions. Then we have a standard value or default value of 1. And this requires that the modifications are verified by means of a 3D load distribution calculation, commonly referred to as loaded tooth contact analysis, LTCA. This is available in Keysoft as well. Second option is that helical gear sets have modifications, but those are applied based on experience, means by a thumb rule or by prior projects and so on. Therefore, it is assumed they are less suitable and the factor increases from 1 to 1.07. And if there's no modification, the factor increases to 1.2. And this factor actually is a linear relationship to the permissible torque, not to the stress level. It's linear to the torque. Means if you have designed a gear set and you now apply this new factor as per revision 2019, and you do not apply any modifications on the gear set, you will lose 20% of the permissible torque, which is quite dramatic. The recommendation is quite simple here. Use Keysoft loaded tooth contact analysis, use the optimization function in Keysoft to find suitable profile and lead modification, and then you're back to the current state, and you may use a factor FZCA of unity. With these 2 comments on part 1 and part 2, we now move on to part 3 for gear root strength. As mentioned before, this revision of the ISO standard 2019 is already available in the next release of Keysoft in parallel to the prior revision 2006, which allows you to compare the results very efficiently and conveniently. Now, if you take a step back and look at the basics of the root strength calculation, just as a refresher, I guess you will rehearse these formulas every night when you go to bed. It's one of our favorite sets of formulas. We find that the nominal root stress is a product of the tangential force, the phase width module, and then these 5 Y factors. In the next few minutes and pages, we will look at these 3 factors, YF, the form factor, YS, the stress correction factor, and Y beta, the helix angle factor. These are the three factors that have changed, or the way that they are calculated has changed in revision 2019. So this will be the focus. Note also that for the two-fruit stress, K gamma has been introduced in the formula. Obviously, we have used it all the time. It simply was not stated explicitly. And then we will have also one influence that affects the permissible stress. That is the relative notch coefficient for one particular material. So most of the time we will look at the stress side, means how are the calculated stresses influenced? And only once we will briefly look at the permissible stress side. Now let me give you an overview of what has changed with respect to part 3 of the ISO standard on the root strength. Let us start with the form factor. Number 1, the first influence is there is a new factor, F epsilon, that considers the influence, the positive influence of a higher contact ratio, in particular of a higher transverse contact ratio on the calculated stress. If, for example, we have a gear set, let's say a spur gear set with a contact ratio well above 2, then the load is always distributed between two pairs of teeth. Basically, each pair has only half. This effect was not fully considered in prior revisions, and this new factor now takes into account the positive effect. Secondly, for internal gears, the root shape is now calculated based on the tool data. Means the shape-ring cutter is described by means of its addendum, dedendum, number of teeth, profile shift, and, important, the tip rounding, the curvature at the tip. This influences the radius in the root of internal gears in prior revision of the ISO 6336. This calculation was simply inaccurate. This has now been much improved. Third point, we will look at the influence of the profile shift. Specifically, which profile shift is used for the calculation of the root strength, for the calculation of the form factor, and for the calculation of the stress correction factor. These 3 points all influence the resulting stress, not the strength. So this is on the stress level side. Next point we look at is the helix angle factor. The helix angle factor considers the stress reduction due to the oblique angle of the contact lines as a function of the helix angle at the reference circle, beta, and the resulting overlap ratio. This also affects the resulting stress, not the strength. Finally, we will look at the small influence of the relative notch sensitivity factor for one particular material. This is then a small effect on the permissible stress side. So most of the time, we will look at the stresses that are effectively present in the root of the gear. Now let us look at the individual factors. We start with the form factor YF, and we compare the situation in 2006 revision versus 2009 revision. In 2006 revision, the form factor YF is calculated for the nominal 2 form with the theoretical profile shift. In the image here on the right side, you see the theoretical 2 form in pink color. theoretical two form is the two form that gives you a backlash-free condition, sometimes referred to as tight mesh or theoretical gear. In reality, however, we want to have some backlash and we reduce the two thickness. In revision 2006, this reduction in two thickness was only considered if the reduction in two thickness is more than 5% of the normal module, which is quite a bit. So usually for a two thickness tolerance, for example, CD25, that would not be effective. Means in the very most cases, as per the 2006 revision, the cross-sectional property here at the 30 degrees tangent point were calculated with the pink shape for the nominal geometry. Now in 2019 revision, however, the lowest two thickness here in blue color is used. This means the profile shift is not used as the theoretical profile shift, but as the smallest generating profile shift, XE min. Means this blue shape resulting from the smallest manufacturing profile shift is now used to calculate the two thickness properties here down in the root, influencing the form factor. Also influenced is the stress correction factor YS. In Kisssoft, this option to either use the nominal two thickness or the lowest or the mean or the upper in the tolerance band was available for the last couple of years. Some differences to other software therefore could be calculated, and there are other software, for example SD Plus from Germany, that also used that also considered the two thickness tolerances even in the past. A second aspect in the two form factor YF that changed. If you look at the 2006 revision and you look at the formula for the form factor YF, you find an expression in the nominator, you find an expression in the denominator, and that's it. If you look at the same formula in the revision 2019, the same expression as in 2016 is multiplied by this new factor f epsilon. This new factor f epsilon is taking into account that for high contact ratio gears, high contact ratio, sometimes abbreviated as HCR, that the effect, the positive effect of the higher contact ratio by experience is more than predicted by the standard. So from experience being for high contact ratio gears, strength is more than predicted by the standard, it was concluded that this additional factor should be introduced to reflect measurements more precisely. A side note, this factor f epsilon much depends on the contact ratio of the virtual spur gear. The virtual spur gear is indicated by the index N. The contact ratio of the virtual spur gear is equal to the transverse contact ratio of the gear divided by the square of the cosine of the base helix angle. Since beta is a small, typically a smallish positive number, cosinus of this number is slightly below 1. If you take the square, you get again slightly lower than the single cosinus beta. So this factor F epsilon did not exist in 2006, resulting in the 2006 revision being somewhat on the conservative side for high contact ratio gear. And in 2019, it is introduced, and it says it should, it's supposed to give more precise results if the contact ratio of the virtual spur gear exceeds a value of 2. A value of 2 is typically a design that you try to achieve, be it in automotive transmissions, be it in a wind turbine gearbox, or even in plastic gears. Contact ratio in the virtual spur gear more than 2 can be achieved either by having a high helix angle and a corresponding phase width, or a high transverse contact ratio, or both. If the contact ratio of the virtual spur gear is less than 2, then the factor F epsilon is calculated in a different way. Let us look at the different cases for which F epsilon is calculated. First of all, look at these two cases here on the right side, the first two cases. It says if epsilon beta, and here as well, if epsilon beta and means here we are talking spur gears. Epsilon beta is 0 means helix angle is 0. If we have a helix angle of 0 and epsilon alpha n is less than 2, it also means that epsilon alpha is less than 2. Means if we have a spur gear of a transverse contact ratio less than 2, then the value for F epsilon is unity, means no effect. So basically, for spur gears with transverse contact ratio less than 2, there's no change between 2006 and 2019 revision. If, however, your spur gear has a transverse contact ratio higher than 2, then the value immediately, pay attention, immediately drops to 0.7. This jump, this very strict distinguishing between less than 2, equal or more than 2, this is something that we will take up in the ISO committee. This is clearly not realistic. If we have a helical gear that has a contact ratio on the virtual spur gear less than 2, then this factor F epsilon is calculated as shown in this formula. If we have a helical gear, but contact ratio of the virtual spur gear is higher than 2, then we have a very similar formula. The difference being here we have 1 time epsilon beta, whereas here we have half of epsilon beta in this subtraction. Means from this formula, we get 1 minus epsilon beta square root. This will give a higher value, and we will actually have a stress increase because we multiply F epsilon with this expression giving YF, and YF linearly increases the stress. Whereas in the second formula, we reduce only by epsilon beta divided by 2. Therefore, this gives a lower value. Therefore, we see a higher positive influence of the effect. If we now plot the values for F epsilon as a function of the virtual contact ratio, the contact ratio of the virtual spur gear versus the overlap ratio epsilon beta, we see here at 2.0 this distinctive jump from value less than 1 or equal 1 or higher values to 0.7 or less. Values here on the left side, for example, less contact ratio than 1.3 is unusual, typically poor gear design if you have very low number of teeth and no helix angle. We see a smooth transition here. We see a smooth transition here, and only here at the contact ratio 2, we see a step function. You are probably familiar with our fine sizing function that can also be used to simulate such effect. Let us first look at the spur gear, beta is 0, and what we do is we change or modify the addendum of the gear and the dedendum of the gear simultaneously, thereby changing the transverse contact ratio. In the fine sizing function down here, you see the vertical axis is the root safety factor, the horizontal axis is the transverse contact ratio, and in color you see the flank safety factors. The flank safety factors change obviously because we change the tooth height. In 2006 revision of the standard, you could see there's no influence or drastic influence of the contact ratio, whereas in 2019 version, you see a most drastic influence of the contact ratio. At the value of 2, you see a sudden increase of the safety factor from approximately, let's say 3 to approximately 4. Why 3 to 4? If you have a value of here f epsilon about 0.7, whereas here it was 1 because it didn't exist in the 2016 version. If you take a value of 3 and divide it by 0.7, 3 divided by 0.7 is approximately 4. That's why we have this sudden increase in the safety factor. Not realistic. If we now have a moderate or a typical helix angle, let's say 15 degrees, then we still see a fairly noticeable transition at a contact ratio of about 1.8. Why 1.8? Because the contact ratio of the virtual spur gear compared to the contact ratio in transverse section is about 0.94. Therefore, it should be about 1.88 theoretically. If we keep on increasing the helix angle, now beta 35, as for example in a turbo gear set or an automotive transmission, then you do not see much of an influence anymore of this transition depending on the contact ratio. The distribution of the solutions or the safety factor is rather smooth, but you can see the highest values are higher than in the previous version, and the lowest values are lower than in the previous version of the standard, indicating that the effect of the helix angle is more pronounced. If it goes up more. If it goes down more. It's more pronounced. Let us move on to the next topic. That's the form factor as a function of the tool shape. In 2006 version of the ISO standard, the root shape was calculated using a virtual basic rack. In the 2019 version, it is now much more accurate. The property of the internal gear is shown in green here, at the root is calculated by a meshing simulation with the tool being a shaping cutter. The formulas in the 2006 version were not accurate. In the 2019 version, the formulas from the VDI guideline 2737, which was elaborated or is based on theory developed at the University in Dresden, is implemented. This calculation method is now much more accurate. Just a side note, I'm referring to the influence of the shaping cutter on the shape of the internal gear and the strength of the internal gear. However, the standard also permits to use shaping cutter definitions for the generation of external gears. That's also possible. In the course of this presentation, we look at internal gears only. What is the finding? Let us look at this table. In this table, we look at here in red color, the resulting root radii calculated with ISO 6336 2006 edition, considering the Corrigendum 2007. There, in the examples we looked at, we found values 0.4, 0.4, 0.3, 0.3. However, if we looked into the Kissling graphics, which is based on the simulation with the shaping cutter, we found that the true radii are far smaller, resulting in a higher stress concentration. This has been improved in the 2019 version of ISO 6336, and here in bold black, you have the root radii in the internal gear compared to those of 2006 version. And you can see there's a significant reduction in the root radii by 20%, 40%, and so on. Obviously, this will lead to a higher stress concentration or a lower strength. Now, let us look at the helix angle factor Y beta. The Y beta takes into account the influence, the positive influence of oblique contact lines. Note that beta is limited to 30 degrees and epsilon beta is limited to unity. On the left side, you see 2006 version, Y beta as a function of the helix angle, the horizontal axis, and the contact ratio, the different lines. In 2019, you can see the graphic looks completely different. Note that the change in epsilon beta in 2019 version somewhat counteracts to the influence of F epsilon explained above. The purpose of changing the formulas for Y beta was to have the influence of the helix angle to be less. You can see there's an additional term here, 1 divided by cosine of to the third power of beta. Cosine beta is less than 1, means this factor will actually increase. Means the stress goes up, means the strength goes down. If we plot Y beta again as a function of beta itself, the helix angle, and the overlap contact ratio, you get again a field like this with high positive numbers for high helix angle but low contact ratio. That's a very unusual design that you normally don't have. Again, more easy to visualize is if you use the fine sizing function in Kissling. On the right side, what you see that the high safety factors have virtually disappeared. Why so? That is because the influence or the positive influence of a high helix angle was over predicted in 2006 version. In 2019 version, this over amplification of the effect of the strength was reduced, therefore resulting safety factors go down. Sometimes you find counterintuitive results. For example, in 2006 version, each number here signifies a gear design with safety factors. In 2019 version calculation, the whole image looks different. Our conclusion, or the message that we want to convey to you with this example, is it's difficult. It's difficult to predict what happens. You really have to run calculations. The effects are counteracting each other and make it difficult to predict by gut feeling. Then on the permissible strength, the permissible stress side, on the strength side, there's only a small influence for GTS material, that's black malleable cast iron of prolific structure. You may have know a trade name, ADI. There, this material has been added, and the SN curve in the static domain is influenced somewhat. Small detail, not so relevant. In conclusion, most of the significant changes are on the stress side, not on the strength side. Now let us implement this method, the 2019 method, with some examples, and let's see on an empirical approach what changes. Let us start with 4 wind gearboxes. We have designs A, B, C, D, European companies and 1 Chinese company. The wind gearboxes have power range 3.1 megawatt, 3 megawatt, 7.5 megawatt, 3.3 megawatt. The first has 3 stages, planetary helical, second 2, third 3 stages. Let us look at the first example, and that's the one that we will discuss extensively. The next few we will proceed more quickly. We have here the first stage, 4 planet, intermediate stage, 3 planets, output stage, 1 parallel stage, and we have calculated this gearbox once using 2006 revision, once using 2019 revision. We have plotted the results in blue color, the results from 2006 revision versus in green color, the results from 2019 revision, and in gray color, the change. For the sun and planet of the first stage, we see that the resulting safety factor goes up. For example, from 2.25 to 2.45, an increase by 9%. Why so? Typical wind gearbox design have epsilon beta in the first stage, the overlap contact ratio, approximately 1. Epsilon alpha, the transverse contact ratio, is typically 1.6, which is about, for this small helix angle of about 6 degrees, equal to the contact ratio of the virtual spur gear. And typically in the low speed stage, we have beta of maybe 6 degrees. Therefore, cosine of beta is almost equal to 1. If you now look back onto page 22, with epsilon beta 1, that's the horizontal line here, and a helix angle of about 6, we find that Y beta is approximately 0.96. On the other hand, if you look onto page 13 to determine F epsilon factor, we have epsilon beta about 1, this horizontal line, and the virtual contact ratio, or the contact ratio of the virtual spur gear, approximately 6, and we find a value of about 0.79, which means that if epsilon is about 0.79, Y beta is about 0.96. Let me scroll back to the example. So we have a drop in Y beta. We have a drop in YF in the form factor because F epsilon has dropped from 1 to 0.79, which means that both effects are to our favor, and we have a significant increase in calculated strength. On the other hand, we observe that for the ring gear, here of the low speed stage, the safety factor has dropped from 1.69 to 1.58. This is now because the root rounding in the ring gear is calculated more accurately and typically drops. Let me go back to that particular slide to remind you. So in the past, the radius in the root of the ring gear was calculated as per an inaccurate set of formulas. This has been changed, but the values drop. Therefore, we have a higher stress concentration. Therefore, we have a lower safety factor in the root of ring gears. Again, more safety factor on the external gears, less on the ring gear. The picture repeats itself for the other stages. We have compared this to other wind gearboxes and found a similar picture. Here a design originating from Finland with 4 planets, approximately same diameter to phase width ratio. A different design here, this is a spur gear design in a wind turbine, not typical. You can see that the transverse contact ratio is less than 2. You can observe there's a drop, a small drop in the safety factor in the planet and the sun by about 2%. Why? This is because now the tooth thickness is calculated for the smallest manufacturing profile shift and not for the theoretical profile shift. Therefore, tooth thickness goes down and we have a higher stress, a higher bending stress. Also, for the internal gear, we now observe a significant reduction in the safety factor. This is again the influence of the smaller root rounding radius due to the more accurate calculation, which is originally based on VDI 2737. One more candidate, same picture, same mechanism. In this particular example, we found that the change in the result was almost 20% in the predicted safety factor. If you're familiar with the certification guidelines, you know that a change of 20% is a whole new story in gearbox design. This means the requirements of certification guidelines will have to change. Yeah? Just because we get a different result does not mean that the gearbox can transmit more torque. We just get a different calculation result. Now let us leave the wind industry to itself and go on to another modern topic, EV transmission. We have calculated an EV transmission, a 2-speed EV transmission, using a planetary gear set attached to the motor and 2 parallel stages. And we find a similar picture for external gears of high contact ratio. And that's what you do in an EV transmission to keep vibrations low. You see that the root strength increase, or the calculated root strength rather, not the root strength, that's a physical property of the gearbox, but the calculated root strength increases here by 15%, for example. And for the ring gear, we have the same effect. The calculated strength drops because the calculation of the root radius is more accurate and a lower value is found. You can also observe that for the flank strength, the factor that compares results 2006 to 2019 is unity. This is what I mentioned previously. We focus on the root strength, and the factor FCZA is unity in all these examples. Finally, we look at the 8 examples from ISO TR 6336 part 30. These are sort of the official cases to verify software or your own calculation or a spreadsheet. Some of these examples are not so typical applications, for example, extremely high speed or extremely low speed or double helical from unusual materials. Still, it gives a good overview to compare a software to a reference calculation. Same picture, you see in green color 2006 root calculation, in blue color 2019 root, in light gray the change, and in magenta and turquoise for the flank, and in dark gray the change. And we found that the root safety factors changed when using the 2019 version. They dropped in some cases. That's noticeable. they can also drop by 3%, and they increased by 16%. Again, the statement is it's very difficult to predict by gut feeling, will the results go up or down? Such calculations that we have shown in the previous slides can be automatized using Keysoft scripting language. Here we have the example script that was elaborated by my colleague, Mr. Langhart, to run the calculations that we have shown you previously. Basically, the script takes a certain model, calculates it as per the 2006 revision, calculates it as per the 19 revisions, and exports the results to a spreadsheet, and that's how we elaborated these slides. Finally, and almost on time, let me conclude as follows. A word of caution. The conclusions that we present here are preliminary. We have played with a number of examples. We have seen that the changes were to the negative, to the positive, plus 20%, minus 3%, and we found it's really difficult to predict because some effects are fighting each other. If, say, one factor goes up, another one goes down, and you can't really predict easily which one wins. In tendency, we found that for helical gears, in tendency, root safety factor increases, the calculated root safety factor. We also found that for helical gears, that the influence of a higher transverse contact ratio is stronger compared to the previous revision of the standard. For spur gears, external spur gears, we found that the safety factor drops slightly, the root safety factor, because we look at the smaller tooth thickness because we consider the tooth thickness tolerances. For internal spur gears, the safety factor drops considerably because of the smaller root rounding. And for spur gears with a high contact ratio, more than 2, there's a step function in the safety factor. We do not like this step function. We do not believe it to be realistic. That is our preliminary conclusions. The recommendation to you is gain experience using this 2019 revision. How? Run calculations with 2006 revisions of gear sets known to you. Take the same Keysoft file and run it again with 2019 revision and compare the results. That's the only way for you to gain experience comparing and using these two revisions. Ladies and gentlemen, thank you for taking your time to listen to this presentation. This is a most fascinating topic to all of us, and it will keep us busy for the next couple of years since it has implications on the design, on certification, and also on the contractual side. Thank you. My name is Hanspeter Dinner. I'm Director Global Sales with Keysoft AG.
Thank you very much, Hanspeter. There have been a few questions we can address. And the first question is regarding loaded tooth contact analysis. So if we perform a loaded tooth contact analysis, does this effect of F epsilon is also considerable in the fine sizing if it's done with contact analysis?
That's a tricky question because you combine three things, the contact analysis, F epsilon, and the fine sizing. The answer is yes, because in the contact analysis, we do look at the load distribution among pairs of teeth. So implicitly, this factor F epsilon is considered in the loaded tooth contact analysis. And if you link the fine sizing function to the loaded tooth contact analysis, it's still the loaded tooth contact analysis working along the same principle. So the answer is yes. Excuse me, I have to admit, we haven't done this combination yet, these three effects. Yeah.
Thank you, Hanspeter. We have another question here. Do these changes in the ISO imply that it is better to have a HCR gears rather than having high helical angle for tooth strength and stress? However, how are we sure that this has not a contrary effect on flange strength?
Again, a very good question. I mentioned on one of the earlier pages this factor that has been introduced for part 2, this, what is it called, FCA set. Now, if you do a contact analysis, a loaded tooth contact analysis in the whole planar faction, you will notice that at the start and end of mesh, you have a distinctive stress peak if there's no modifications. Means on the flank, at the start and end of mesh, you have a stress peak if you have helical gears. And the higher the helix angle, the more pronounced it is. However, the permissible stresses were measured on spur gears where there is no such effect. And to account for this means that there's a stress peak for helical gears if you do a loaded tooth contact analysis, but this was not considered in ISO. This new factor FCA set was introduced. So the answer again is yes, because there's one more factor on part 2 that tells you that the helical or the high helix angle also has a disadvantage on the flank.
Thank you, Hanspeter. We do not have that much time anymore, but we will address 2 last questions, and the other questions will be then covered by email. So one of the last questions is, it was mentioned that a 30% stress drop due to the FE of F epsilon of 0.7 is not realistic. Now, will this be open to revision in the standardization process in future?
Yes, everything is open to revision and we will address it. There's one huge disadvantage. It takes years to become effective as a new revision. However, it may be, or that's what we try to propose, that's what we will propose, to issue a corrigendum such that this step function is replaced by a gradual function.
Okay, thank you, Hanspeter. And the last one. So if you get a plus 20% margin for the gears being designed, do you recommend them to redesign the whole gearbox, or how should be this addressed?
No, that's exactly the dangerous part. It's only the calculation that gives you 20% more strength, but the gearbox will have the same strength as yesterday. The gearbox doesn't know that there's a revision of the standard. So the obvious question is the new standard more accurate? We believe so. Accurate in the sense, does it reflect reality? We believe so. However, everything is also related, or what is relevant is that you couple these calculations with experience. Therefore, the recommendation, run calculations with both methods, compare the results. Because in your existing gearboxes, you may have experience. Yes, this gearbox was really at the limit of the strength. And if you then recalculate it with 2019, you get the reference point. So the important thing really is run calculations twice, compare the results, gain experience. That's the task ahead for all of us.
So with these words, we would like to say a huge thank you for all who participated in this web demo. We have over 500 participants, and we stay in touch, and all the questions that have not been answered will be answered then by email. We wish you to stay healthy and take care of yourself. Bye all.